Good morning everyone, and welcome to today's worked exam answer question. Today I'm having another look at a transition metal question but with a different focus. So today we are thinking a little bit about how various ligands can bind to transition metals to make complex ions, and then in the second part on the back we're having a think about how we can conduct a redox titration to find out some information about a particular salt containing iron 2 in this case. So as always, I will highlight information, I will do my worked answers, and I will explain every step that I have taken along the way. Okie dokie, so the first questions on here are thinking about the bonding within this solid iron 2 ethane dioate dihydrate, and we're shown 2 repeating units in the polymer chain for this polymeric structure. Now we've got some arrows on there, we've got our iron at the centre. It also says each ion is also bonded to 2 water molecules that are not shown in the diagram. So that would suggest that the shape around the iron 2 plus ion is octahedral, and it asks us first and foremost to name the type of bond that is represented by the arrows, and arrows are used to show special types of covalent bond, which are our coordinate or dative covalent bonds. And these are where, rather than each atom sharing 1 electron to a covalent bond, one atom will share both of the 2 electrons within the pair and the other atom will be sharing none. That's essentially then when it's getting you to explain in part B, because it says explain in terms of electrons how the water molecules, which are not shown in the diagram, form bonds to the iron. So how does that work? So basically you are explaining how coordinate bonding or dative covalent bonding works. And back in the structure and bonding topic in year 12, hopefully you were told that anytime you have got a dative covalent or a coordinate bond, you need to specify which which atom has the lone pair, and then say which atom it's essentially donating it to. So I've written the oxygen atom within each of the 2 water molecules has a lone pair of electrons, which they then donate to the iron. That's a very standard answer for any time you are explaining coordinate or dative covalent bonding. Then it says, predict the value of the bond angle between the 2 bonds to iron that are formed by these 2 water molecules. So if the iron is bonded to 6 things, including the 4 oxygens that we can see in the diagram and the 2 oxygens of the water molecules that we can't see in the diagram, the 4 in the diagram I'm taking to be like flat in the plane of the paper and be separated by 90 degrees, and thus them to be like our equatorial positions in our octahedral shape. So they're the ones that go around the middle, like the equator goes around the middle of the Earth. I would therefore suggest that the water molecules are going to be axial, and that means kind of up and down, straight through the middle, sort of like that. And that's why we can't show those on the diagram, because one of the waters will be sat directly above the iron and the other one would be sat directly below the iron, because of how we've chosen to draw this, or they've chosen to draw this. In an exam, if you're drawing octahedral, you would tend to put your axial bonds like that, and then you'd have your wedges for 2 of your equatorial bonds coming forward, and then you'd have your dashes to your 2 equatorial bonds going back into the plane of the paper. So I think if our water molecules are being our axial bonds, that those 2 bonds from the water molecules will be 180 degrees apart from each other, and they would then be 90 degrees apart from these equatorial bonds that we've got on here. But it specifically wants the bond angle between the 2 bonds to the iron that are formed by the water molecules. So how far apart they are, which I think is 180 degrees. In the second part of the question, which is part D, we're thinking about a redox titration. So it tells us that the iron 2 ethane dioate dihydrate can be analysed by titration using potassium manganate 7 ions in acidic solution. In this reaction, the manganate 7 ions oxidise the iron 2 ions and the ethane dioate ions. So within the iron ethane dioate, and they've repeated the formula here for us, we've got the iron 2 plus, which can be oxidised to iron 3 plus, but we've also got the C2O4, which can be oxidised to CO2. So the manganate ions are going to, as we're told, oxidise both of those things. Now they've written the equations for us to show A, how the manganate ions get reduced, and I know that that is a reduction reaction, one, because the electrons being gained are on the left of the equation, but also two, the oxidation state of the manganate is decreasing from +7 in the MnO4 minus, and we know it was +7 because again in the name we were told manganate VII ions, which is the Roman numerals for 7. In the product, the manganese ion is in the +2 oxidation state, so that's gone down by 5. And the iron and the ethane dioate ion are both being oxidised, and I know that again because looking at where the electrons are, they are on the right hand side now, but also we've got an increase in oxidation state in both of those examples as well. We're then given a lot of mathematical information, which we're going to need in the second part of this. So we're told that we've got a 1.381 gram sample of impure iron 2 ethane dioate dihydrate, and we've dissolved that in an excess of dilute sulfuric acid and made that up to 250 centimetres cubed of solution. We're then taking a 25 centimetre cubed aliquot of that and titrating it against the potassium manganate, and it decolorises 22.35 centimetres cubed of a 0.0193 mole per decimetre cube solution of said potassium manganate. First thing we have to do is use these equations that they've given us to calculate the reacting ratio of moles of the manganate 7 ions to the moles of the iron 2 ethane dioate. Now, like with any redox equation, the key thing is that our electrons being gained and our electrons being lost balance. And at the moment, the manganate ion needs to gain 5 electrons each. The iron ion only releases 1, and the ethane dioate ion only releases 2. So we've got a total of 3 electrons being lost and 5 being gained. 5 and 3 don't balance out. So therefore, we need to find a number that both 5 and 3 go into, which is 15, and multiply up our equations accordingly. So to get my top equation to give me 15 electrons on the left-hand side, everything would be multiplied by 3 in this equation, giving me 3 MnO4 minus. And then here, these two ions come from the same compound. So we've written the equations separately, but we're basically looking for the total number of these compounds. And for every one compound, you've got one Fe, 2 plus ion, which can be oxidized, and one C2O4 minus, C2O4 2 minus ion, that can also be oxidized. In total, those 3 electrons, to make them up to 15, we need to times that by 5. So we're going to need 5 Fe2 plus ions and 5 of the C2O4 2 minus ions. So we're going to need in total 5 moles of the iron 2 ethane dioate salt. That's really helpful for us when we're doing a redox titration, and we always need to write balanced half equations and then a balanced redox equation in order to get the reacting moles between the substance that is being reduced and the substance that is being oxidized. And we have that ratio now of 3 to 5. Notice how in part II it says if you've been unable to answer part DI, you may assume that 3 moles of manganate 7 ions react with 7 moles of iron 2 ethane dioate. This is not the correct ratio. AQA are very good at doing this, in that if you need part I to do part II, if you have failed to answer it at all, they will give you an answer that you can then carry forwards. So if you were not sure how to use these equations to work out the reacting ratio, you can then still get full marks for the second part of this question, which is out of 5, because you would have the ratio, instead of being 3 to 5, as 3 to 7. If you get an answer, I know myself, when I was doing my exams, if I got an answer but then they gave me a different one, I was tempted to not trust that my answer was correct, and I always wanted to use the one that they had given me. I would advise against that. Don't worry if your answer is wrong, because you will still get error carried forward marks. So let's say in part I we got the ratio is 3 to 4. If you then carried that through to part 2 and you used your 3 to 4 ratio in the correct way, you can still get full marks on part II. So it's only if you haven't been able to get any answer at all that I would ever be saying to use the new values that AQA have provided. Anyway, what are we actually being asked to do? We're asked to calculate the percentage by mass of the FeC2O4.2H2O in the original sample. And the key word here is that it told us that the sample was impure. So we want to know, by doing this redox titration, how much of that 1.381 grams is actually the iron 2 ethane dioate dihydrate, and how much of it is impurity that won't go on and react in the titration. And that's the key thing. It is only going to be the FeC2O4.2H2O that is going to react with the manganate ions. The impurities will not. So if we then work backwards from the last piece of information we were given, which was about the potassium manganate, we can then get a mass for the FeC2O4.2H2O that reacts with that amount of manganate. We can then work out the moles in the 250 centimeters cubed solution. Then we can get a mass from the MR and then compare that mass to the mass of the impure sample. And that's exactly what I've done down here. So the moles of the manganate ions, we were given a volume in centimetres cubed. I've divided it by 1,000 and I've timesed it by the concentration to get 4.314 times 10 to the minus 4 moles. This is where the ratio then comes in. We've got the moles of the manganate ions, so we need to then divide that by 3 to get 1 part, and then times it by 5 to get the number of moles of the FeC2O4, which is what I've done there. And that gave me 7.189 times 10 to the minus 4 moles in 25 centimetres cubed, because it says that 25 centimetre cube portion of the solution reacted with the potassium manganate in that way. In the sentence above, it says that they made up the solution to 250, and this is standard titration procedure. You're not just going to make 25 centimetres cubed, because you are going to want to repeat the experiment a number of times, get concordant results. You're going to have to rinse your apparatus. You're going to do a rough experiment run through first. So we always make quite a big vat of solution, and in this case it's 250 centimetres cubed. So if we've worked out the moles in the 25 centimetre cubed portion, we need to times it by 10 to get the moles in the original 250 centimetres cubed of solution, which I've done here, to get me 7.189 times 10 to the minus 3. Then I need to times that by the MR, and I did that on my calculator and I've forgotten to write that number in there, but I will write that in and show you it in a second. The MR worked out from adding up the iron, the 2 carbons, the 4 oxygens, the 4 hydrogens and the 2 oxygens from the water, times that by the number of moles, which gave me 1.293 grams. And then to get the percentage by mass, we need the mass of the impure sample, which is 1.381 grams. And we're going to do 1.293 as the mass of the iron ethane dioate dihydrate divided by the mass of the impure sample times 100, and that tells me that 93.6% of that impure substance was the actual substance that we wanted to have to do the reaction. I will very quickly work out the MR and come back and show you what that is for there. My sincere apologies for that. On my calculator, I always do answer times bracket, and then I just put in all the relative atomic masses for all the different elements, because I like to keep the whole calculator display as I'm working through my calculations. So apologies that 179.8 wasn't there before. That's the MR of this, which enabled us to get the mass, and then we could do the percentage by mass. I think this is quite a tricky question, particularly because both the Fe2 plus and the C2O42 minus ion are getting oxidized at the same time. So you might be caught out and do a ratio of 3 to 10, because if you need 5 of these and 5 of these, but actually because they're in the same compound, we only need 5. I've made that mistake before, so don't worry if that was your first thought here either, but hopefully you understand why it is 3 to 5 and not 3 to 10. If you're not sure, ask, and if there's any other questions that I can answer, please leave a comment on this video on any of my social media pages or YouTube, or drop me an email. Thanks guys!